Welcome to this first lecture in week 7. So I'll just reprise some stuff that we have learned during phase change in unary. So we discussed unary systems, right? And in an unary system we discussed something called phase change. So phase change and phase equilibrium in unary system. So we looked at these. So for phase change, as you know, and we also looked at the phase diagrams in unary systems, and we remember that the phase diagrams we drew in, usually you can draw different types of phase diagrams, mu t, vt, but in general the phase diagrams that are drawn are having pressure as the y-axis and temperature as the x-axis, and we also saw some sort of like a triple points and all this stuff, and we looked at means how the phases will coexist and all. And we, if you remember, we told that we introduced Clausius-Clapeyron equation, and we told that the dp dt, that is the slope of the phase boundary here for any transformation. Say for example you have three phases, you have say gamma phase here, alpha phase here, beta phase. So gamma is here and beta is here. So you are telling that in such a case, gamma alpha phase boundary or gamma beta phase boundary or alpha beta phase boundary, the slopes will be given by Clausius-Clapeyron equation. Okay, so this is something that we discussed, but I just want to reprise because we want to see for different types of systems. For example, system that contains only condensed phases, like for example solid liquid transformation, or let us look at liquid vapor transformation or solid vapor transformation such as sublimation. How does the phase boundary slope, how does the slope of the phase boundary change? Okay, so we have to look at what is the slope of the phase boundary. This is basically a reprise of the last lecture. So slope of the phase boundary, how do you calculate? You first know that if two phases are in coexistence, right, or they are in equilibrium, alpha and beta are in equilibrium, then G alpha has to be equal to G beta. G alpha, the free energy of alpha phase, has to be equal to the free energy of the beta phase at any given pressure temperature combination which is along the phase boundary, right? So basically here, so let us look at these points. So for example, if I am looking at a point here, alpha and beta are in coexistence at this temperature, and at this pressure, right? This is the pressure, this is the temperature at which at this point alpha and beta are in equilibrium. Again, let us look at this point. If you look at this point, and then this is the pressure and this is the temperature, right, at which alpha and beta will be in equilibrium, right? So for example, or say for example at this point, again you have this pressure and this is your temperature, right, that at this point. So along the phase boundary, all points represent the equilibrium between alpha and beta, right, along the phase boundary, all points, each point along the phase boundary, points represent equilibrium between alpha and beta, and the equilibrium between alpha and beta corresponds to a certain pressure and a certain temperature. So if in such a case, as you know, G alpha equals to G beta, now you have only it's a unary system. So it's a unary system, that means you are basically if you are looking at partial means if you are looking at the chemical potential is nothing but the, so in this case the chemical potential of alpha, say chemical potential of some component, there is no other component, there is only one component. So the chemical potential is nothing but, mu is nothing but Gm, that is the molar free energy, right? Mu is basically molar free energy. So mu alpha, that means is the molar free energy of alpha phase, equals to molar free energy of beta phase. Now as you know that d mu alpha, this is something that we know, right, that means this is from the dg equals to vdp minus s dt, right? We know dg, we have done this dg equals to VdP minus SDT. See, there is a plus mu dn, but here n equal to means that basically there is only one component. So if I divide by n, then what we get? If I divide by n is the number of moles of that component, then dg by n, which is basically g by n here is nothing but mu equal to Vm. Vm basically is the molar volume, Vm dP minus S dt, or you can also write Sm dt. S basically the small s, lowercase s basically represents the entropy per mole, right? So the entropy per mole. So this is coming from dg equals to Vdp minus SDT. Okay, so if I have, and then you have also mu dn here, but as you know that you have only n moles of component 1. So if you divide by n on all sides, then basically n by n is nothing but 1 and d of 1 is 0, right? So basically d mu equals to Vm dP minus lowercase s dt, and lowercase s represents the molar entropy. So basically mu alpha represents molar Gibbs free energy of alpha phase. This is molar entropy of alpha phase. This is molar volume of alpha phase. Similarly for beta, this is molar Gibbs free energy of beta phase, molar entropy of beta phase, and molar volume of beta phase. And you have d mu alpha equals to d mu beta. D mu alpha equals to d mu beta. So you get minus S alpha dt alpha. So if this is so, then these equal to this, right? These and these are equal. So this equals to this. So if that is so, minus S alpha dt alpha plus Vm alpha dp alpha equals to minus S beta dt beta plus Vm beta dp beta. Now as you know, at equilibrium the pressures have to be equal, right? For all phases, all the phases that are existing, the pressures have to be equal, right? There should be no difference in pressure, right? If you remove all the internal constraints, right? This we have proved for different subsystems or different phases that are basically separated by phase boundaries, and these phase boundaries are basically like constraints, and if you remove all internal constraints, basically you make the boundary flexible, that is responsive to volume change, and the boundary is diathermal, and the boundary is permeable to diffusion or mass transfer. Again, here there is no mass transfer because there is only one component or one species available, but this comes from mechanical equilibrium, right? This is basically nothing but the mechanical equilibrium, that pressures. So since alpha and beta are in equilibrium, therefore the pressures inside alpha and inside beta have to be equal when alpha and beta are in equilibrium. Similarly, there is thermal equilibrium, right? So this is coming from mechanical equilibrium. And this is coming from thermal equilibrium. Now, see, there is no additional species. This is a unary system. So you have only mechanical and thermal equilibrium to consider, right? Because the chemical equilibrium, which is for each species, is not required, right? Here it is not required. It's a unary system. Now, if you see, then P alpha and P beta are basically same as P, right? Some common value P, and T alpha and T beta are equal, and they are equal to some common value T. So then, if you rearrange, you get this. Vm beta minus Vm alpha dP equals to S beta minus S alpha dt. So now Vm beta minus Vm alpha is delta Vm alpha to beta, right? Vm beta minus Vm alpha is basically, according to our convention, that is the delta Vm, that is change in molar volume when there is a transformation from alpha to beta, right? Delta Vm alpha to beta. Note that, this is very important to note, delta Vm alpha to beta is just the negative of delta Vm, according to our convention, beta to alpha. Because alpha to beta means, the way we calculate alpha to beta, basically, so Yeah, so delta Vm alpha to beta equals to minus delta Vm beta to alpha, and delta Vm alpha to beta is nothing but Vm beta minus Vm alpha, while this is equal to, so this is this, and this is basically Vm alpha minus Vm beta. See, look at the arrow sign. If you look at the arrow sign, then you will see, so beta to alpha, so it is like, so basically beta to alpha transformation, how much is the volume change? So then what we are doing, Vm alpha minus Vm beta. If it is alpha to beta transformation, it is Vm beta minus Vm alpha. I think now you are very clear with this. So if you are clear, then you see, if you arrange this, right, so here we are looking at Vm beta minus Vm alpha, which is basically delta Vm alpha to beta, right, because final is final minus initial, or you can think of like final state minus initial state. Obviously, remember, this is at the transformation temperature, at a given pressure, at different pressures and temperatures. Basically, alpha and beta are in equilibrium, right? It's a reversible equilibrium along the phase boundary, right? Both are in coexistence. But depending on the convention, so you can use delta Vm beta to alpha, then this will be also delta S beta to alpha, right? Delta is that means entropy of transformation, molar entropy of transformation from beta to alpha to beta, or you can write it as beta to alpha. So it does not really matter. So this is basically what I am trying to say is that if you write this way, delta S beta to alpha and delta Vm beta to alpha, it does not really matter, because the negative sign that is there on both sides, on the numerator there is a negative sign, on the denominator there is a negative sign, so they are basically getting cancelled out, and this is called the famous Clausius-Clapeyron equation, and that is the equation of the phase boundary, right? It gives the slope of the phase boundary. As you can see again, that this is pressure temperature, and the slope of the phase boundary, is this one, right? I go to any point, and if I have to draw a slope, I will draw a tangent, right? And that tangent line will make a slope, and that is the slope, right? This is the slope, and that slope is nothing but dp by dt, right? Because you have pressure, y and x are, so if you have y and x, so this is y axis, this is x axis, dy dx is the slope, right, of the xy curve. So dy dx at any point is the slope of the xy curve. So exactly that's what we have written. dp dt is the slope of the pressure temperature, the pressure temperature curve that delineates the phase boundary, right? So the phase boundary that delineates the equilibrium coexistence between alpha and beta basically has a slope of dp by dt, which is given by the ratio of molar entropy of transformation from alpha to beta or beta to alpha by the ratio, the molar volume, the change in molar volume during transformation from beta to alpha or from alpha to beta, right? So this is the ratio. So the slope depends on this ratio. Now let us think of the solid liquid boundary. First let us look at the solid liquid boundary. So you can, at the solid liquid boundary, at different pressures you will have different melting or freezing point, right? You can call it either melting point or freezing point, again because it's a reversible thing. So as alpha, say for example alpha is solid and beta is liquid, so if solid transforms to liquid, it's called melting, and while liquid transforms to solid, it's called freezing, right? So now again mu alpha equals to mu beta. Now mu alpha is nothing but H alpha minus Ts alpha. Again, H alpha is the enthalpy per mole of alpha, H beta is enthalpy per mole of beta, and S is entropy per mole of alpha, and S beta is entropy per mole of beta. So as you can see, H beta minus H alpha equals to T S beta minus S alpha. Now what is this T? This T is the temperature at which alpha and beta are in equilibrium, and in solid liquid bound, in the solid liquid coexistence, the temperature at which they are in equilibrium at different pressures are called the melting point or the freezing point, right? So basically this T is going to be, this T, you can call it Tm, or you can call it also T transformation, right? T transformation, TTR or Tm, right? This is the T. But what you are saying is H beta minus H alpha. See, there is a nice relation that you get. H beta minus H alpha, that is the enthalpy of transformation from alpha to beta, right? Enthalpy of transformation from alpha to beta equals to T times entropy of transformation from alpha to beta. Again, each quantity is calculated per mole. Okay, so basically now you can rewrite this as dp by dt equals delta s alpha to beta to delta vm alpha to beta. Now delta s you are replacing by delta h alpha to beta by t delta vm alpha to beta. What is t? T is basically TTR or TM. Now basically remember TM0, let us call TM0. So let us think of this as TM0 is the melting temperature at pressure P0. That means TM0 is the equilibrium or coexistence temperature between alpha and beta, solid phase and liquid phase, and that is nothing but the melting temperature or freezing temperature. Similarly, let us consider Tm as the melting temperature or freezing temperature or the coexistence temperature or the transformation temperature at pressure at some pressure P. Now, if we assume that delta H alpha beta and delta Vm alpha beta do not vary with T, then we can just integrate Clausius-Clapeyron equation. So remember, so that's why I avoided writing TTR, because you have this dt and dt by t, and then I will put this limits, right? Dt by t. So instead of writing here directly TTR, we know that this is the transformation temperature. This T is the transformation temperature at different pressures, right? T is transformation temperature at pressure P. At some pressure P prime, say, let us. At some pressure P prime. Okay, maybe we can call it T prime and put a T prime. So T prime is transformation temperature at pressure P prime. Now, if you see, you have this dt by t or dt prime by t prime. So basically, this is like ln t, and here you have p, and you have p minus p0. And as I told you, delta H alpha beta and delta Vm alpha beta, if we assume that they do not vary with pressure or temperature, and this is it is reasonable because both are condensed phases, so there is not much change with pressure. So there is PV work is negligible, right? So as a result, you can just write it as so this integral can be written from this equation. From this equation, you can write this integral, right? This integral. And you can put the limits Tm0, Tm. As you can see, when it is Tm0, pressure is P0, and when it is Tm, pressure is P. So if you now plug it in, you get P equals to P0 plus delta H alpha to beta by delta Vm alpha to beta ln Tm by Tm0, right? So if Tm by Tm0, if Tm minus Tm0 is small, then ln Tm by Tm0 can be approximated as ln 1 plus Tm minus Tm0 by Tm0, and basically I take only the linear term because Tm minus Tm0 is small. I take only the linear term. It is like ln 1 plus x. So if I do ln 1 plus x, where x is small, we can write this as x plus x square by 2 factorial and stuff. But x is small, so x square will be even smaller. So basically I can just take the first term, there is a linear term in the expansion, which is Tm minus Tm0 by Tm0, and that is basically Tm minus Tm0 is nothing but the change in melting temperature due to change in pressure. So change in melting temperature due to change in pressure. Now you can see a very nice relation you get, P minus P0, so basically which is like delta P. So I can write this as delta P equals to delta H alpha to beta, and then I can put a temperature Tm0, okay, so that is my reference temperature, and this is delta Vm alpha to beta into delta Tm. So you can basically, if I know the change in melting temperature, I can estimate the change in pressure, or if it is change in pressure, I can estimate the change in melting temperature. Basically, I can directly write dp dt as delta H by T delta V, and if delta H and T delta V are basically if delta H and delta V are independent of temperature, so they come out of the integration, right? They come out of the integration. But if you want to do more generalized integration, for example, you think of this epsilon to beta transformation in titanium, epsilon to beta. So epsilon is HCP phase, okay, at lower temperature you have epsilon phase, and at higher temperatures, okay, and for different pressures you can have BCC phase. So you have HCP phase, you have BCC phase, and there is a transformation temperature Ti. Okay, now if you think of this, now let us write this way. So what is the, in the pressure temperature diagram, what is the slope? Delta Hm, that is the molar enthalpy of transformation from epsilon to beta, divided by T. T is the transition temperature, times delta Vm, that is the change in molar volume from epsilon to beta, right? So now delta LHM epsilon to beta is again, as I don't want to confuse you, and it's a function of temperature and pressure. Note that this can be, so we told in the last approximation that let us assume that delta H alpha to beta is not a function of temperature and pressure. Delta Vm is not a function of pressure and temperature. So then it becomes a very, very simple relation, right? This relation, right? Many a times we use this relation. However, if we tell no, delta Hm is a function of temperature and pressure, that is, it will also change with temperature and pressure. So basically, what does it mean? Hm beta is also a function of temperature and pressure, and Hm epsilon is also a function of temperature and pressure. Now, if that is so, now you have delta Hm epsilon to beta is nothing but Hm beta minus Hm epsilon, right? This is how we have looked at, right? Beta is the final state, this is the initial state, so this will be final minus initial. Now, if I do differential, that is d of delta Hm is dHm minus dHm beta minus dHm epsilon. Now dH, again this comes from applying Maxwell's relation and doing further simplification. Okay, so I'll take so if you do this approximation, so I'll just skip once. I just want to tell you what is the genesis of this. So if you want to see that, you can think of, by the way, this is something I haven't told. So it is something that is used. I haven't told this previously when I taught Maxwell's relation, that you have to basically, ultimately Maxwell's relation is basically equating the second derivatives, right? So if you look at Maxwell, so it's called Maxwell relations. So Max Born, basically when he looked at this Maxwell relations, and I think you are also having some difficulty in remembering, right? Because you have to equate stuff. So basically this, so Max Born created this mnemonics. There are 100 versions of this. There are different versions of this. So he created this mnemonics where he starts from G and he goes, this is a thermodynamic square. So you go, good physicists have studied under very fine teachers. So you can see G, P, H, S. Good physicists have studied under very fine teachers, right? So if you look at that, now if you see, then if I want to go for say I want to write a differential, say I take this H, okay, I take this H, I directly get V. So when I use H, I will take the two signs here. So dH equals to VdP plus, so you have TdS, right? You have VdP plus TdS, right? And also you can look at, so remember in the differential, so when it comes to the only differential thing that comes in is here. So the sign of the differential, so minus s is there, so there is a d of minus s, and there is a VdP here and TdS here. As you can see here, H has S and P here and V and T here. So V will come here and T will come here. See, both are positive. But when it comes to differentials, you ignore the sign. Okay, you ignore the sign. So you get VdP plus TdS. Again, when you have differentials, you ignore the sign. So del S del Pt is equal to, so if you see this, del S del Pt equals to minus del V del T. Why minus? Because P is now not a part of the differential, right? P is not a part of the differential. But if you can see this, when I am looking at del S del P, okay, and then I am fixing, when I am looking at these, then I am fixing this, right? So del S del P T equals to, now I have this, right? If I have this, then I will take this. So this becomes del V del T, but there is a minus P, because if I take the opposite one, then I have a negative sign here. So this becomes minus del V del T of P, right? Now you know ds is del S del T. So I have taken basically this thing. So I have taken S is a function of temperature and pressure. Then I am basically using the exact differential. So I am writing ds equals del S del T dt plus del S del P dP. Again, del S del T is evaluated at constant pressure, and del S del T P we have already shown, and it's very easy. So it comes from here, dH equals to TdS, right, which is equal to Cp dt. So basically, if dH is TdS, then basically del S by del T, right? So because TdS is Cp dt, so ds by dt is Cp by T, or del S by del T equal to Cp by T at constant pressure, right? At constant pressure. So now this is equals to minus del V del Tp, which comes from the Maxwell relation, minus del V del Tp, and that is nothing but, because alpha is nothing but alpha equal to 1 by V del T P, right? And this comes out to be, so then this becomes minus del V del Tp. Again, remember, when you apply thermodynamic square, only in the constant terms that you are having here, you are applying the signs, right, the negative signs. Otherwise, it is just you ignore the signs, and del S del P is nothing but del V del T. You can do it for various cases, and you can equate the second the second derivatives, and you can see that you can derive all the Maxwell's relations. But you go for the simplification, because what I have done, I have expressed this now, del S del P I have expressed in terms of measurable quantity, del S del T I have expressed in terms of measurable quantities, right? This is all measurable, this is all measurable. So then I write dH, right, which is TdS, right? ds I am now expressing this, right? This is basically nothing but ds. So TdS plus VdP. So basically this is, so you have Cp dt, Cp dt, T into T times 1 by T, this cancels. So basically this becomes Cp dt, and this is minus V alpha, and this is, there is a V here, there is a V minus V alpha multiplied by T. So I can take V common, and it becomes 1 minus T alpha T. So basically, as you can see here, dH is Cp dt plus V 1 minus T alpha Tp. Now if that is so, you apply this relation, and you get back. So basically I am going back to the slide here. So this is nothing but, this is the relation that I have used, right? And remember what I have done, I have differentiated the delta Hm, right? So delta Hm is nothing but differentiated dHm beta, dHm epsilon. So d delta Hm epsilon to beta is nothing but delta Cp dt, right? This has a delta Cp, right? Because dH equals to Cp dt, but this is epsilon to beta. So delta Cp is Cp beta minus Cp epsilon. See, Cp, the heat capacity at constant pressure of the beta phase, and heat capacity of constant pressure of the epsilon phase, and you have delta Cp dt plus delta V into 1 minus T alpha dP. Now as you can see, for condensed phases, delta, this change in molar volume, this quantity, change in this quantity is Vm beta 1 minus T alpha beta, and this is Vm epsilon 1 minus T alpha epsilon. For condensed phases, this term is very, very negligible, right? Because the pressure changes up to 10 to the power 5 bar, which is like 10 GPa. So up to 10 GPa pressure, you can neglect this term. Up to 10 GPa pressure, you can neglect this term. Basically, the term associated with dP can be neglected, because the change in pressure, unless you go to like 10 GPa, you do not have a very big influence of that. So then basically, practically, for condensed phases, dH is nothing but Cp dt. But here, as you can see, dH is a function of Cp and T, and Cp itself, by the way, can be a function of temperature, right? Cp itself, so basically d delta H epsilon to beta, that is this is the enthalpy of transformation, the molar enthalpy. So if I can put like here m, then this becomes molar heat capacity. So the d delta Hm, that is the differential of the entropy of transformation from epsilon to beta, is nothing but delta Cp molar. This is the change, the change in molar heat capacity when phase transforms from epsilon to beta times dt, right? So basically now Cp we can write, so for each phase we can write Cp is nothing but A plus Bt plus C by T square plus dt square. This comes from experimental data. See, I am giving you recipes to calculate even when things become slightly more complex in terms of dependencies, but the calculations are quite straightforward. So only thing you have to calculate, when you calculate, you have to be patient, and you have to calculate terms correctly, right? So basically, if you look at delta Cp according to this expression, then delta Cp is the difference in Cp between the epsilon phase and the beta phase, or between the two coexisting phases, which is basically nothing but the difference in the coefficient A, difference in the coefficient B times T, difference in the coefficient C by T square, and difference in the coefficient D times T square, right? This is times T square, remember this is by T square, okay? So now if I do from T naught, which is some reference temperature, to T d delta H, then this is basically delta Cpt dt, which comes out to be this, right? So if you do this, delta A plus delta Bt plus delta C, so then delta H at some temperature T minus delta H at some temperature T naught, which is the reference state, I can write this as delta A times T, delta B times T square by 2, delta, and this will be delta C by T square, so this is minus delta C by T, and delta D by T cube, delta D into T cube by 3, right? And again this has to be put as T and T naught. So if I do that, so basically I get the change in the change in enthalpy during the transformation as a function of the coefficients that we have determined experimentally of the heat capacities of the coexisting phases. That is, here in this case it is epsilon and beta, right? So if I do that, then the relation just becomes, and delta V epsilon to beta is nothing but V beta minus V epsilon, okay, right, V beta minus V epsilon, which can be a function of temperature and pressure, but if we neglect that, so this just becomes a constant, right? Because I told that V into 1 minus T alpha, you can delta V in 1 minus T alpha can be neglected for a solid liquid coexistence. So then this becomes P minus P naught. There is a change in pressure from the reference pressure is equals to this by basically, so this is the delta H by and there is a temperature, if you remember. So if you can see here, delta T was there, the T, and there is T and T naught, and this becomes just delta V epsilon to beta. So basically this is coming from this relation. What is the relation? This relation, right? You can simplify this relation. You can finally write this relation as after integration. So we have to do the integration. So basically previously my integration was this, right? This was my integration, where delta H as well as delta Vm were independent of temperature and pressure. However, if delta H itself is a function of temperature, then only thing that changes is the numerator, right? Then the numerator is changing, and you have P minus P. Okay, so please check the expression derived by yourself and make sure that you are doing it correctly, so that if I can also if you do this little bit of algebra, sometimes there is always possibility that you can make some mistake here and there. You please check it and confirm that what I am getting here, when delta H is a function of temperature and pressure, and Cp is also a function of temperature and temperature, right? By the way, what we told, delta H can be a function of temperature and pressure, but the pressure term we have neglected. So delta H here is a function of temperature, but delta H is related to the heat capacities, or the differences in the heat capacities of the two coexisting phases, and his capacities also can be functions of temperature. So you look at the differences and then you basically plug it in and you get this relation. You please check this relation. Okay, this is for a more generalized approach. In general, you will often see the problems are such that the temperature ranges are such that the delta H mostly may be independent of temperature and pressure. However, if the temperature range is slightly larger and you have RCP variation, then you have to take into account of that. And basically, if you have even the molar volume variation, that also has to be taken into account. But see, these are calculations, and thermodynamics gives you a way to calculate all these changes in the phase boundary. How the phase boundary, instead of becoming linear, becomes curved, you can basically know by just looking at this relation. Right, the relation that you have derived for different systems. For example, the epsilon to beta transformation in titanium. Right, so that's the idea. So again, thermodynamics square, I just went there and I told you that it's a very, very useful tool. You can use it, but again, use it cautiously. Remember that in the differentials, these negative signs that are given here are neglected. But in other cases, you have to use this negative signs, right? Say, for example, V, is it negative? No, it is positive. So I have used positive. Temperature, positive. But ds and dp, whether they are negative or positive, the signs in the differential is neglected, right? So this is something that is a take home message, and you can quickly use this and then use your own strategy. See, remember, there are many books with different strategies. They will tell that you do this and then do this, and see, ultimately all the strategies, one important thing is you have to focus on the relation that you want and that you want to use, based on what are the parameters that are known to you, what are the measurable parameters that are known to you. Based on that, you construct the relation, and based on that, you come up with an useful relation, right? So basically, there will be different strategies. You can follow some strategy. Some strategies may work in some cases, and some strategies may not work in some other cases. As a result, your strategy should be to look at the final relation, look at what are the measurable quantities, what are the measurable quantities available. Based on that, how do you approximate all that indirectly measurable quantities? Whether it is change in enthalpy that is important, or it's change in entropy, or change in free energy. This is something you have to basically, looking at the problem in focus, you can basically find out which are important quantities. Now think of liquid vapor boundary. So you have alpha is liquid and beta is vapor, and you are, the process that we are talking about is like evaporation. Liquid to vapor is like evaporation or boiling, and vapor to liquid is like condensation, right? And again you have this equation. Now in general, as you know, that gas has a much larger molar volume compared to the any condensed phase, whether it is liquid or whether it's solid. So basically delta Vm vaporization is nothing but Vm beta, where beta is the gaseous phase, or the, right? So basically you can write this as, so delta Vm can be just represented as, so basically if I do this, then I get delta H vaporization by T Vm beta, right? Vm alpha can be neglected. Now we can think of, and many a times it is indeed a very good approximation, that beta phase, that is the gaseous phase of the vapor phase, okay, above the liquid, is an ideal gas, okay, is approximated as an ideal gas or a perfect gas. Then basically it becomes, life becomes simpler. You get Vm beta equal to, the molar volume of beta can be expressed in terms of the universal gas constant, the temperature, right, the temperature by pressure. So you have, as you can see here, Vm beta is nothing but RT by P, right? Vm beta is nothing but RT by P, right? Because Pvm equals to RT. So then dP by dt equals to delta H vaporization and T times RT by P. So basically, if you calculate a little bit, so this becomes dP by P, right? Because you see, you have RT by P here, so P goes up, right? P goes up. So now this P, when I take this P, so I'll just write here. So dP, this implies dP by dt equals to P delta H by RT square, right? So okay, now you integrate, so it becomes dlnp, this becomes dlnp, and this becomes delta H evaporation by R dt by T square, and at T equal to T naught, let us assume P equals to P naught, that is the reference vapor pressure, and at T equal to T is P equal to P, and then you do the integral, and if you do the integral, you have dt by T square, so dt by T square is minus 1 by T is the integral, right? The integral is minus 1 by T after you do this integral, right? And then you put the limits T naught to T, then you get minus delta H vaporization by R, right? This term, and again remember, we are assuming that delta H vaporization is independent of temperature, right? It does not change with temperature. So basically, if I do that, again, if you want to put in all the dependence of temperature, if the problem demands that, you have to do that, and again the same recipe, the more generalized recipe that I have shown earlier, will follow. So right now it becomes very easy, right? It becomes a very easy integration. So ln P by P naught, where P naught is the reference vapor pressure, is given by minus delta H by R 1 by T minus 1 by T naught. Now look at this consequence. There is a negative sign here, and this is delta H of vaporization. So vaporization is a process in which a liquid will absorb it, which is basically an endothermic process, but you have a negative here. So how does the pressure change with temperature? You can basically find out very easily from this expression, right? Basically you can further simplify this as P equals to, so you are writing P equals to, say for example, P naught e to the power minus chi, or P naught exponential minus chi, right? This e to the power minus chi is basically, you can also write it as exponential. E is nothing but exp, right? So then if you write that way, then as you can see, P by P naught equals to exponential of this entire term, right? Exponential of this term, right? So where chi is nothing but this delta H, so it is e to the power minus chi, right? P0 e to the power minus chi. So chi is nothing but this factor delta H by R, delta H vaporization by R, 1 by T minus 1 by T. For solid vapor boundary, you can go the exactly the same way. Here it is solid to vapor sublimation or deposition, and then you get ln P3 by P3 naught is equals to this term, right? Minus delta H sublimation, that is a change in transformation. Again, this is, we are assuming that delta H sublimation does not depend on temperature. But again, the vapor phase has a much bigger molar volume than the solid phase, and so you end up with the same equation. Only thing, Ts is the temperature of interest for this is the transformation temperature of interest, right? Transformation or sublimation temperature of interest, and Ts naught is the temperature at the reference state, and Ps naught correspondingly is the pressure at the reference state, right? So now think of triple point, right? You often see triple points, right? So basically you have this diagram like this one, and then you have this one and this one. These are the branches, right? So these are the branches. So if I make these guys slightly thicker, so you have one branch like this, and you have one branch like this, and you have one branch like say this. I will not use a blue color, I will use the white color. So you have this, right? So only thing here I have drawn a straight line. Instead of straight line, it should be, so you can approximate this as a straight line also. So if you approximate it as a straight line, but if you do not want to approximate, that's also fine. So you can write this way and think of, so this is your, right? This is your, these are your phase boundaries, right? These are your the thick lines are your phase boundaries. So alpha beta I have drawn linear, but if you want, you can make it also. So you have a nonlinearity here, so I can replace that. So I'll put the alpha beta line here. Is this line, and I can basically take this line. So these thicker lines are your, right? These thicker lines represent your phase boundaries, and these extended lines are basically that extension. These are like some sort of a, you can think of like these are like continuations of this line. So these thick lines are the phase boundaries. So the yellow thick line, as you can see here, the yellow thick line represents the phase boundary between alpha and gamma, right? And this is the alpha plus gamma coexistence, right? This phase boundary has alpha plus gamma coexistence. Please note, you can actually derive the change in the degrees of freedom when you move from the single phase alpha to single phase gamma through this phase boundary, right? So how the degrees of freedom changes. Again, it is for the alpha plus beta or beta plus gamma. This is the beta plus gamma phase boundary, so this is beta gamma. But see, the interesting part here is the triple point. So if you look at that, there is this triple point where This is like a pressure and temperature at which solid, liquid and gas coexist. So at that point you have degree of freedom, as you remember, equal to, degree of freedom F equals to C minus P plus 2. C is the number of components in the unary system, it is 1, minus number of phases is 3 and plus 2, so this is equal to 0. So the triple point, as you remember, was fixed, right? But how do you determine it? Now you see a very interesting idea. So you have alpha phase, which is your solid phase, beta phase, which is your liquid phase, and gamma phase, which is your gaseous phase. As you can see, solid phase has the lowest molar volume or lowest entropy, and your gamma, that is has the highest entropy, right? So gamma appears here, right? And beta, so gamma appears. So if you see, you have alpha phase here, gamma phase here. Gamma phase is your, so this is your beta phase and this is your gamma phase. So gamma phase, as you can see, at higher temperatures gamma phase will be favored, because gamma phase is the gaseous phase which has a much higher entropy in this case, right? So you have now delta V, let us assume now a sublimation, that is basically from alpha solid phase it is going to gamma phase, but we can, so that is basically nothing but Vm gamma. So you can put an M here. I am not putting, but it is implied. It is all per mole is implied. Okay. So basically, if I am doing that, delta V alpha to gamma, which is Vm gamma minus Vm alpha, or V gamma minus V alpha, we can write this as you can see here, V gamma. We can write this as V gamma minus V beta plus V beta minus V alpha. So what I have done, I have just written this as V gamma minus, so I have just added one term minus V beta, and then I have to take it out, right? Minus V beta, then I do plus V beta minus. So it's like I am telling it's a stepwise process. Okay, I am imagining this as a stepwise process. One step is gamma to, so basically beta to gamma transformation, right? Beta to gamma transformation. Another is alpha to beta transformation. So basically I am telling delta V alpha to gamma. So what I am telling is delta V alpha to gamma is going through one process like this, which is beta to gamma transformation, and this is alpha to beta transformation. So basically I am writing this is basically solid to gas is equal to so beta to gamma is like liquid to gas, and this is like solid to liquid. So you have solid to liquid, liquid to gas, which gives you solid to gas transformation. Now as you know that with using this minus e to the power minus chi type of idea, that you can write the, say if this is for the solid vapor equilibrium, so PS, S indicates sublimation process, so you can write PS equals to some coefficient AS exponential minus delta H alpha to gamma by RT, and liquid vapor equilibrium again it is like P vapor equals to AV exponential minus delta H beta to gamma RT, right? This is alpha to gamma. Alpha to gamma is, alpha is solid, gamma is gas, right? Alpha is solid, gamma is gas. So you have this expression. Here it is liquid to vapor, so it is PV and this is AV. So I am just using some coefficient here, and I am using some superscript here to distinguish between this equation and this equation. And you have, obviously the main distinction is here, right? This is delta H alpha to gamma, and here it is delta H beta to gamma. Now at triple point P3 and T3, both these equations are satisfied. Triple point P3 T3 basically satisfies both these equations. So P3 equals to AS times exponential minus delta H alpha to gamma RT3. Similarly, P3 equals to AV exponential minus delta H beta to gamma, right? This is the beta to gamma transformation enthalpy by RT3. So I have substituted T by T3 here and P by P3 here. Similarly, here also I can substitute P by P3 and T by T3, because at the triple point all of these are satisfied, right? Solid vapor is satisfied, equilibrium is satisfied, liquid vapor equilibrium is satisfied, solid liquid equilibrium is satisfied, right? So now if you have this, you have AS, so as you can see here, AS exponential minus this equals to, and you see I am not considering all of these, I don't have to consider that. And as you can see here, AS exponential. So I am doing what? I am taking this term and this term to be equal, right? Because this is P3, this is also P3. So these terms are equal. So if I do that, I get a little bit of manipulation. I get, so basically I do ln as, and then this is exponential. So ln of exponential is only this term, right? And there is ln av and this equation. So you get RT3 ln as by av, because delta h alpha to gamma minus delta h beta to gamma, or basically delta h alpha to gamma minus delta h beta to gamma, which is basically T3. And as you can see here, delta h alpha to gamma, delta h beta to gamma, if you look at that, you can also basically plug in delta h alpha to beta, because the same idea for the molar volume, the same idea will hold, right? Delta h alpha to gamma equals delta h beta to gamma plus delta h alpha to beta, right? So if you have that, so now if you see, you have delta h. So if you just write, say d is the transformation, so delta h d is delta h alpha to gamma minus delta h beta to gamma, right? Delta h alpha to gamma minus delta h beta to gamma. So delta h d ln p3, we just do a little bit of algebraic manipulation. So basically you get delta h d ln p3 is nothing but ln as plus ln as to the power minus delta h beta to gamma, and ln av to the power plus delta h alpha to gamma. You just follow this derivation, then you will see that ln p3 to the power this equation equals to ln as to the power this equation. So as to the power minus delta h beta to gamma, this is plus delta h alpha to gamma. So basically this becomes delta h beta to gamma. So if I rearrange, so I have this term here, right? I have this entire term here in the as the power, and here we have this term and then you have this term. So basically if you separate this out, you get P3. Okay, so you have got T3. Basically you have got T3 already, right? So this is the T3, right? And you just do a little bit of algebraic manipulation and you will get P3 as a function of s to the power delta h beta to gamma minus. So basically you are taking the coefficients, assume the coefficients are known and the AV coefficients are known, and assume the heats of transformation from beta to gamma or alpha to gamma. Beta to gamma is like liquid to gas and alpha to gamma is like solid to gas. If we know all these heats of transformation, you can also get P3, right? You can get P3. Okay, so that's the idea. Okay, so how do you get it? So let us tell. So this is exactly, so this is one example. So remember, this is one equation that I have drawn. So this is an equation that I have derived. Okay, this is one equation that I have derived. So you have, as you can see, you have two equations, you have two unknowns. So basically if you can basically get T3, you should be able to get P3, right? You have two equations, right? So basically P3s are equal, you have made, and you got T3, and once you got T3 you plug it back, right? Once you got this T3 expression, you plug it back and do a systematics, and basically you do some manipulation, algebraic manipulation, you will get into a P3, right? So here AS has to be known. So the idea is here, so if I give such formula, what you are seeing here, what is the take home here? AS has to be known, AV has to be known, and these transformations have to be known. Now I will tell you a very easy way to estimate the triple point. You may not have to, so exponentials actually help you here, because if you have these exponentials, you know that if I can plot log in the p in the log scale, things become easier. Now think of this. One important thing I have to tell you. Say for example, if the liquid is solid is melting to liquid, and a liquid is boiling and it is converting to vapor, obviously the boiling point is always going to be higher than the melting point as long as the pressure. So here I am talking about an axis. If you please note this axis, this is like 1 atmosphere pressure or 1 bar pressure, and this is like 1 10 to the power minus 25 bar pressure. Obviously you can see that this is log scale. So you have 10 to the power minus 25 bar pressure, very low pressure. Then you have moderately low pressure, and this is like the atmospheric pressure. I am not going beyond atmospheric pressure. You see that. Now if you look at this atmospheric pressure, at atmospheric pressure, you know melting point, you know boiling point. In general, at atmospheric pressure, the boiling point has to be greater than the melting point. Okay. Now, one thing, delta H alpha to gamma, that is delta H. This is alpha is basically the solid phase to gaseous phase. Again, I can write the same way, like in steps of 2. So this is delta H alpha to beta, which is basically solid to liquid, and this is liquid to gas, beta to gamma. So you have, say for example, for silicon, this is done for silicon. For silicon, delta H silicon is this, okay, 386 kilojoules per mole. Okay, so this is from liquid to vapor. So silicon from liquid to vapor transformation is 386 kilojoules plus liquid to vapor. Remember, this has to be plus 386 kilojoules per mole, right? So it has to, it's an endothermic process because liquid has to absorb the heat and convert to vapor, like liquid has to absorb the heat. Now this is basically the pressure is 1 atmosphere and T is 2873 Kelvin. Okay, then in that case, if this is the transmission temperature, and then you have AV equals to PV, right? Because see, what I told is, if you look at that, PV equals to AV exponential this. So basically, AV equals to PV exponential, but this minus will become plus. That's all, right? So that's what I have done here.